here's where it gets a little more complicated. When we have a situation where there is an acceleration. For this question, how far did Kyle Busch go during 3 seconds if he started at 60 meters per second and accelerated at a constant 4 meters per second squared? One thing that you've got to recognize here is that if he was accelerating at 4 meters per second squared, he did not end this 3-second period at 60 meters per second. He ended at something significantly higher than 60 meters per second. We should also be able to identify that the 60 meters per second is a velocity, and that this 3 seconds is our delta t. So we can't be fooled here into thinking we can take our 60 meters per second velocity and claim that it's the average velocity over this elapsed time of 3 seconds, because it's not. It must be lower than the average because he ended up going a lot faster because he was accelerating. Therefore, if we want to use this simple equation, we're going to have to figure out what the average velocity is. And I'm going to declare that that would be a pain in the butt. So we're just going to eliminate the possibility of using this equation. Although I guess we could. But this is what the 4 kinematic equations are for. Here's a good kinematic equation that describes position, velocity, time, and acceleration. Sometimes, what really time here is elapsed time. We just have to recognize that sometimes you'll see equations written without the delta, but the delta really should be there if we were to be totally, completely correct. But in any case, this t, or delta t, is 3 seconds. But continuing to translate this from the physics language to a normal language is, let's look at this x. This is a position. That would actually be the final position. And this is x naught with this little 0, sometimes called x naught. That's the initial position. V naught is the initial velocity, and the a is our acceleration, which is 4 meters per second squared. And when we get equations that are this complicated, I highly suggest that we catalog our variables. So usually on the right side of the page, you can just put, a equals whatever number, x equals whatever number, delta t equals whatever number. So here are all our variables and what we know about them. Notice that we weren't given a specific initial position or a final position. So we could just define wherever he started as being point 0 on the coordinate system. And in that case, the final position, x, would be equal to the distance he traveled, and that would be how far he went. Or we can manipulate this equation to make displacement variable appear. Remember, the variable for displacement is delta x. And what is delta x but final position minus initial position? We can get that to appear if we just subtract x naught from both sides. After doing that, this would be our left side, and our right side would just be the same, except it wouldn't have x naught. And we could write this replacing x final minus x initial on the left with delta x, which is how far Kyle Busch went. Let me rewrite everything again. I recommend lots of rewriting of equations as you manipulate them. The more you write what seems to be needless rewriting is really the better you'll do, really, because it seems needless, but it really helps you keep organized, I think. And at this point, we have solved the equation for the variable we are interested in, which is delta x, and we know the identities of all these other variables. So we have numbers that we can put in for v naught, delta t, a, and this is the same, delta t, 3 seconds over here. So we can just plug in those numbers. Check me to make sure I did that right. And our calculator should tell us the final answer. And then we can do a reasonability check on it. 180 here is what he would have traveled if he wasn't accelerating. Then we got an extra 18 because he was accelerating. Let's think about the units. Did the units cancel correctly to give us meters? Yes, here we had seconds divided by seconds, and here we had seconds squared divided by seconds squared. So those canceled. Let's look at this second kinematic equation. And let's manipulate it a bit. First I'm going to subtract v naught from both sides, which is going to have the effect of moving it to the left side. Then we're going to recognize that v final minus v initial is just the change in velocity. And at this point I'm going to point out that we're talking about average velocity here and elapsed time. So I put in a little bar above A to show that it's average and a little triangle delta to show this is a change in time. And we should realize at this point that we've seen these three variables together very recently. I'm going to divide both sides by delta t. When I do that, it shows up on the bottom on the left side, and we're left with acceleration on the right side. This is just saying, I'm going to flip the left to the right and the right to the left. This is just saying average acceleration equals change in velocity over elapsed time. This is the mathematical definition of acceleration that we've already seen before. This is not a new equation. You already know this one. It's just written a little bit differently here. So let's spend no more time on that one. That's boring. Okay, let's look at number 3. We got final position x minus initial position equals final velocity plus initial velocity over 2 times time. That is elapsed time. And let's start to translate this one. We got final position minus initial position. That's delta x, displacement. Now if you have two numbers and you add those two numbers and divide by 2, what you get is the average of those two numbers. So here we have two velocities and we divide them by 2 after adding them together. That is the average of those two velocities, which is the average velocity that whatever object was going over this elapsed time t. So we can really write this whole term as average velocity, v with a bar over it. And then t is just the elapsed time. And look what we're left with here. This is just one of the three ways to write the first equation we saw. This simple equation, velocity equals displacement over elapsed time. So again, this isn't really a new equation. We keep getting gypped here. What's useful to note is that this, v final minus v initial over 2 is a good way to find the average velocity. So we keep getting ripped off. We get promised these new equations, but they're just different forms of the old ones, written different ways. But this last one is kind of a new equation. So this is helpful when you have an acceleration happening and you don't know the elapsed time, or it's not given. We can use this equation perhaps if we have a question like this. What is the acceleration if Chuck Yeager flies from 0 to 335 meters per second, which is the speed of sound, over the distance of 3,000 meters? If you really had this problem on a test or a homework, the hard part would be figuring out what equation to use. But we could do that because we would want to find an equation with a in it, the variable we're going to solve, and these other things we know, such as initial velocity and final velocity and displacement. So the hard part would be finding this equation and realizing that we know everything in it. We know delta x is 3,000, we know this is 335, this is 0, this is 335. We know everything in it except for the variable that we want to solve for. But once we did the hard part and found this equation, we would just use algebra to solve for that variable that we want to know, which is a. So I'm going to start that process by subtracting v0 squared from both sides to try to isolate a. And then I'm going to totally isolate a by dividing both sides by 2 delta x. And I'm going to loop back up to the top of the page here. So we've done the next hard part, which is isolate our variable that we're interested in. And now we just plug in the numbers. And we get this. And when we plug those numbers into the calculator, well, I got 18.7. And every number answer has to come with the units. And I haven't been practicing what I preach. I didn't put in units for all these numbers. So I am now. I just did. And we can see that we have meters squared over seconds squared, and we divide that by meters to give us meters per second squared. So at this point, it's probably still a good idea to check that the units cancel to make sure you did things right. But as you get more and more comfortable with using these type of equations, if you're pretty darn sure you use the equation correctly, you might eventually be able to not put in the units in this part, but you'll still need to answer with units. And the little trick I like to use sometimes is that I know that if I used all SI units here, velocity is meters per second in SI units, distance is meters. If I use all SI units in the numbers in the problem, my answer is going to be in the SI unit. So here I would have known that I could have used the SI unit for acceleration, which is meters per second squared.
Made with Doodlecast Pro.